Okay, hi everyone, and welcome to today's session. Today we'll be touching on a very recent and interesting topic known as DeepSeek R1. So basically, a China company surprised the world by releasing a model almost as good as GPT-O1 model, which is an impressive breakthrough because this is an open source model, which means that anyone can take a look at their weights. They even explored their training process in a paper. So I think they did a lot of service for the open source community. And that's why today we'll be spending some time to dissect this DeepSeek R1 paper and see some of the insights that they have here to see how we can build better and better learning systems to build better large language models. So if you know my previous sessions, I myself think that large language models is not the final solution. It will be part of the solution of an architecture that can self-learn. So that includes memory, that includes having different functions like verifiers and so on. But having a good base large language model is very important. And here, DeepSeek R1 manages to self-improve by just simply doing reinforcement learning on certain benchmarks, collecting trajectories, and they use a very innovative procedure known as Group Relative Policy Optimisation, where they just sample the model like n times. And then based on these samples, they rank it with a verifier. And basically, those that score above the group average will be reinforced. And those trajectories that score below the group average will be negatively reinforced. What this means is that we will keep trying to do better and better actions relative to the group average. So it's pretty cool. Let's delve more into that as we go through the paper. And yep, let's begin. So the first slide here is just to show that DeepSeek R1 shares almost on par performance with O1, which is really impressive for an open source model. Okay, there's a lot of other benchmarks, but I don't need to go through because feel free to read the paper yourself for all the comparisons. This is not the focus for today. All right, so how do you use DeepSeek? Just some primers in case you don't already know. You can go chat.deepseek.com and then it's free to use here. You click on R1, you can use R1. You can try it out for yourself. There's also a DeepSeek app. And also, there's also other platforms that are hosting DeepSeek because DeepSeek is open source. Many different platforms like Hugging Face have already hosted their own versions of DeepSeek. So if you are worried that your information might be taken by a China company, no worries. There are other free versions of DeepSeek you can use. You can even host it on your own computer, the distilled model, the smaller model. All right. So DeepSeek doesn't have structured outputs yet. So just want to do some advertisement for my agentic framework, AgentJo. So what you can do is you can just put in your own LM function. And what you do is you just need to put a system prompt and user prompt. Over here, you just define your own LM. Here, I use the API version of DeepSeek. Okay, after that, you can just use whatever output format you want here. Just put the keys and the values and also put the type here if you need. And then out comes the structured output. So yeah, if you need a structured output format to use with DeepSeek, or basically any LM of your own, feel free to use this. There's also an agentic framework as well. So what you can do is you can create a Python function, put in the variables here, and then in your function description, just put your variable names here. And what will happen is you will interpret this function, just assign the function to your agent, put the agent name, agent description, put in your LM. Here's DeepSeek. Okay, then you just run with your tasks. And you can see that here we have a chain of thought where we have observations, thoughts, and actions. And we'll run the task. So here we book 2 appointments, one with Paul, one with Sally. You can see that it booked according to the format required. So yeah, if you want to use DeepSeek for, agentic framework, just consider this. Okay, that's all for the advertisement. All right, let's move to the main point of the paper. So what is DeepSeek? DeepSeek basically builds on their previous model called DeepSeek V3 base. And basically what they do is they employ this group relative policy optimization in order to improve the model performance in reasoning. So the base model itself is actually quite competitive, but it's nowhere near the O1 level. It's like 10 to 20 percentage points difference. So this group relative policy optimization process is quite significant because it helped to bridge the gap between V3 and GPT-O1. Okay, just a caveat. There's actually a small amount of cold start data. A small amount, I also don't know how much it is, but there's a significant amount of cold start data. What is cold start data? Basically, the reinforcement process doesn't start from scratch. The model already has some form of idea about how to do certain things. And how is because they already did some fine-tuning, supervised fine-tuning with good trajectories. All right, and they did not really say where these good trajectories come from, based on my knowledge, but it's likely taken from models such as O1, all right, as a cold start trajectory. Okay, so let me see. There's something in the chat. Oh, okay, nothing. All right, so this RL process, let's analyze a bit more today what this RL is. So the idea is after you do the RL process, you can do self-improvement. Okay, this is quite cool, right? What you do is after you create your own DeepSeek DeepSeek R1, you can take trajectories from this trained model, do a filtering process to take only those trajectories that are good. And you can distill a new model. Over here, they distilled a new V3 base. So their distillation is more SFT data set for DeepSeek V3. All right. And this DeepSeek V3 will then be used to apply reinforcement learning again for the next version of DeepSeek R1. So they keep doing and doing and doing. So the more they do reinforcement learning to the model, they sample trajectories from it, take the good ones, train the base model again, then do RL again. So it's really cool because through an iterative process of this kind of self-improvement, they managed to get quite good results. All right, so this is essentially the key slide that we need to go through today. After you look at this slide, that's it for today already. The key idea is very, very simple. It's so simple that I think it's remarkable that it works so well. Okay, so the idea is you pit all the trajectories in the competition. All right, so over here you can see these different robots. I got GPT-4 to generate this. Basically, this is DALL-E3 that generated. And what this shows is that you have different trajectories, and then you have a ranker, right? The ranker will say, hey, this trajectory is good, this trajectory is bad. So like maybe these three trajectories, very good, okay? They perform very well. Learn more from them, okay? Train your model, fine-tune your model so that it repeats these trajectories more often, right? Then on the other hand, we also have some trajectories that are bad. Okay, these are the bad ones. What do you do when they are bad? Of course, if they are bad, you don't really want to learn them anymore, right? So we try to take away those trajectories by, letting the probabilities of such tokens be lower and lower. Okay, so we don't want to output such tokens. These trajectories, we want to output these tokens more and more. And all these are done using an unbiased selection process. How? This is done like for math, you have the ground truth data. So like for your AIME data set, for I think the math data set, you have your answers. You can compare whether the trajectory has achieved those answers. If they have achieved those answers, you can give them a good score. If they don't achieve the answers, you give them a bad score. All right, that's for math. Programming tasks, how do you know whether they achieve it? So if you use like stuff like code forces, code forces is a competitive programming competition. So if you go to have this kind of data set, you actually have the test set as well. You can use the test examples to see whether your code runs correctly, right? So of course you could do different reward models. Like if your code compiles, you have one reward of one. If your code can solve training set, maybe you have reward of three. Code can solve test set, reward of five. Yeah, I don't exactly know what reward model they use, but you can easily see that with such a rule-based approach to select the trajectories, only the good trajectories will be reinforced. All right, just a key question here, right? How do you do such reinforcement if you don't have the ground truth? Anyone wants to do a like this is the difficult question. So right now I'm talking about math and code that have a ground truth. We can check whether it's correct. Anyone want to give a shot? Like if let's say we don't have the ground truth, how can we use this method? Okay, this is a tough question. So I think the main thing is you can't really know for sure, okay? If you don't have the ground truth, you'll be guessing, all right? So you might use an LM as a judge to see whether or not your trajectory is correct or not. But you might suffer from the bootstrap error, which means that your LM as a judge may not be that accurate, right? So over here, we have very, very grounded, very, you are assured that the answer is correct kind of validation. And this is important for learning because we don't want to reinforce a trajectory that is potentially wrong. So all these trajectories that are reinforced, they are all likely correct. Okay, why I say it's likely correct? Because you only look at the answer. Your reasoning process might be wrong. Okay, but as what I talked about in previous videos, if your reasoning process is wrong, it doesn't mean that it's a bad thing. Okay, what it means is that as long as you can get the right answer, even your reasoning is a bit flawed, as long as it's flawed consistently, you get the answer, and that's more important, right? So I always like to say that, even humans, we also don't reason very well. We may not reason correctly, but what matters is the outcome. So I like this process a lot. All right. Any questions so far? Because this is the key slide for today. All good. Maybe give me a thumbs up if you're okay. All right. So we go into a bit of the math. All right. So this GRPO, I'll emphasize a bit more because I think this is the crux of DeepSeek R1. So what exactly is Group Relative Policy Optimization, right? You can view it as a kind of competition-based learning. We choose the best trajectories to learn from, okay, that are above average, and don't repeat the worst trajectories. And the quite food for thought is, can this work even without the RL process? All right, so we discuss this later at the end. But let's just delve into the equation. And you can see that this is the kind of loss function, the objective that they're trying to maximize. Okay, and what this objective is this expectation is a very complicated equation. Actually, it's a very simple thing. Average out across all possible questions and sample G times for each question. All right, so this is an expected, means like you keep running this objective across all possible questions. You can see that this thing means take Q from the distribution of PQ, which means the question distribution. Right, so this is why I don't really like math. Actually, this is a very simple equation. Boom, became so complicated with this. All right, and this is actually the second one here is the crux. Okay, so what you do is this is a variant of the PPO. Okay, proximal policy optimization. Okay, which means that we modify our policy but don't modify too much. Okay, so it's very funny because what they show is that, if you suddenly change your landscape, right? If let's say this is your loss landscape for your policy, all right, this is your maybe your theta, and then this is your loss or your loss of your theta, right? What happens if you change your parameters too much? There might be some valleys here. So whenever you want to change something, right, you just want to go gradually nearby. Okay, so we may not like basically you don't want to go into a case whereby okay, here the loss is okay, maybe we don't call it loss, we call it J, okay, which means that we want to increase it. All right, so if you go slowly, all right, in a region that you're familiar with, okay, yeah, you can go a bit more. But if you are going to a region that you're not too familiar with, you don't really want to go here because it's lower. All right, you want to go slowly. So there's some clip. Okay, clip means I don't go too much. Okay, sorry, the clip is here. All right, so we want to limit the exploration of your landscape, subject to, whether or not, like, is it too much or too little. So you don't suddenly shift so much. You shift a little bit at a time so that you don't suddenly jump into something worse. All right, so this is the intuition behind proximal policy optimization. You move your policy, but you subject to certain restrictions. Right, and one of the restrictions that you subject to is also whether or not your new policy is very, very different from your old one. So there's this term here called KL divergence, which means that, if my policy is too different from the other one, then this term will be very, very high. If your policy is very, very close, your new policy is very close to your original policy, then this term will be close to zero. All right, so this is basically some bias that you give so that, you don't explore too much. All right. Okay, so the exact equation looks very complicated. The intuition is very simple. The intuition is that you want to change your policy, but you don't want to change it too much. Right? And I realize I haven't explained policy to y'all. So let me just explain what's policy right now. So what's a policy in RL? Okay, in policy is like this. You have a certain, maybe you take in a certain state, and then you have a model, and then you come up with action. So the policy means that if you have a policy pi theta, and then you take a policy pi theta given a state, you should get an action. This is the traditional RL formulation of policy. So basically, when you have a certain state, you want to query the model and ask it, what action will you do at this state? So traditional robot simulation is like this. Let's say you are in the top left cell. Okay, are you going to go right? Are you going to go down? The action is something like that. Or the robot arm, this is your robot start state. Is your arm going up? Arm going down, right? If you translate to LM terms, this state is your context that you have. And this action maybe is your next token. So this is used also in like ChatGPT. They have a PPO step for the RHF and so on. Yep. So this is adaptation of reinforcement learning to large language models. And essentially this policy network is just a neural network. So essentially what this whole equation means is that given a certain state, a start state, which means like certain questions, my output trajectory, my response, okay, I want it to be a certain response. And I can do that by biasing the gradients a bit. Okay, so if my probability for this token is higher, so let's say initially for this question one, maybe I'll give answer A 30% of the time. I'll give answer B 70% of the time. This is my initial. Okay, let me just put this somewhere. I don't know where to put here. Let's say I feel like, okay, based on what I see. Okay, let me just change this. Based on what I see, answer A is better. So how? I basically tell my model, okay, I want to output answer A more often, right? So basically, I change my probabilities. So now I make maybe my answer A 51% of the time, answer B 49% of the time. So by changing your gradients, okay, if you increase your gradients for a certain token, you increase the chance of that token being output. Likewise, if you decrease the token probabilities, you decrease the chance of it being output. So by doing some form of massaging of the gradients here, you can actually influence your answer outputs. So initially, maybe my answer is not good. Okay, I want to bias to answer A. I make my gradients move such that my output for answer A appears more often. Okay, and how do we do this? This is very, very, very important. Take a look here. Take a look here. Okay, I'm going to delete everything here. Because I want to highlight this thing here. Okay, so anyone can tell me what this A is? What does it mean? Okay, you are quite quiet today, but so this is the advantage term. Okay, and this advantage term typically in like proximal policy optimization, this advantage term will just tell you how much better is your answer to a critic, right? So over here, there's no critic. Okay, over here, the critic is quite ingenious. The critic is everyone, right? That's quite cool, right? I mean, if you take a look here, you are using everyone else as your critic. See, look at this group of outputs here, O1 to OG. This is, you sample the model G times. And you use the average score. This R means like you go through a verifier, they give you a certain, they basically give you a certain score. You take the average score, and you take your current score here, you minus off the average score, and you divide by a standard deviation. This is actually to like compress the reward. But the main thing is that if your RI, let's say you are a score of 10, okay, and your average maybe is 5, it means my advantage term will be positive. and what this means. Okay, if my advantage term is positive, if my advantage term is positive, okay, let me just write in words here. If advantage term is positive, I bias my gradients to produce that token more. If advantage term is negative, I bias my gradients to produce that token less. And that is essentially the cool part of it, because this advantage is weighted against every other response. So it's really cool, because what you really do is you don't have the answer, you don't have the ground truth. I mean, sorry, you don't have the good trajectory, but you have a lot of different people. You have a lot. You have trajectory A, trajectory B, trajectory C. Okay, let me just put this properly. Trajectory C. Oh, why is it not going there? Okay, trajectory C, trajectory D. Each of them, you give a certain score, like 5, 5. Okay, maybe I don't do 5, 5, 7, 9, 11. So each of them have a certain score, and the average score here is 8, right? So what this means, you can essentially see that these two trajectories are above average. If you take this score and you minus the average, this will give you positive advantage. And likewise, if you take the 5 and you minus 8, 7 minus 8, this will actually be negative. So this will be a negative advantage. And you can see all this based on this equation here. What this means is that certain trajectories that are bad, okay, bad by the verifier compared to the group average, I decrease their token probabilities. I don't output them so much. While trajectories that are good here, like 9 and 10, I output them even more. All right. And the interesting thing about this reinforcement process is this. You actually reinforce very, very good trajectories more than this one. So let's say if I have an 11 and a 9, I actually reinforce trajectory D much more than trajectory C. Anyone want to give like a guess why is that so? Maybe I pause here for a while. Like why in this equation do we reinforce trajectory D more than trajectory C? Anyone want to give a shot? Derek, are you there? You understand? Okay, no worries. Yeah. So basically, if you look at this equation over here, um, you have a certain score here, and you minus off the mean. So if your score is higher, let's say your score is 11, our R is 11 compared to R is 9, your advantage term is actually higher. So this is actually a larger term. And what this means is that if you take this whole equation here, you will actually update the gradients more. Okay, of course, subject to whether is it familiar gradients and subject to some clipping as well. So um, this basically is the crux of the algorithm. And I quite like the key aspect of this algorithm, that you reinforce trajectories based on an average, and you reinforce the better trajectories more than you would for an okay trajectory. And of course, this trajectory will be reinforced very negatively compared to this trajectory here. Okay, questions here? Any questions? All right, let's move on. Okay, I spent quite some time here because I think this is actually more or less the main thing for DeepSeek R1. All right, so the other thing for DeepSeek is that in order to generate good trajectories, you kind of need to, because your base kind of data set doesn't really contain chain of thought. Like those data sets online, usually, like if you have certain things like, question, like your data set might be something like this. Question, what is 1 plus 1 maybe? And the answer is 2. All right, so normally the data set in the wild does not contain chain of thought, usually. Okay, maybe it has changed right now. So what we want to do is we want to make this data set become a little more elaborative. So it's like, maybe if you want to ask like, what is 1 plus 1? My answer will be, I take 1 and add 1, and this results in 2. So this is your thoughts, your think. And then you have your answer. Hence, the answer is 2. So essentially, we are doing a chain of thought by basically putting this prompt to generate the answers for DeepSeek. Okay, so instead of just answering directly, we ask the model to do some thought process, and then after that, do the answer. And then, this whole trajectory that's output will then be used for fine-tuning again to improve the model. So we essentially imbue some form of thoughts inside the answer. And by selecting those answers that are correct, hopefully the thoughts are correct. So these thoughts can again be used later on to solve other problems. So this is the prompt that is used. And the question that I have is like, okay, why not use JSON output to say that, hey, instead of just doing HTML text like this, why not just do like, thoughts, something, and then answer something. So I did think about this, and actually to me, it doesn't really matter how you do it. As long as you have a proper format for the LM to output thoughts and then the answer, you can do it in HTML text, you can do it in JSON. Maybe HTML text has an advantage in the sense that because in JSON, whenever inside this quotation marks, you want to do stuff like quotation marks, you need to do a backslash, or you need to do backslash, like basically you need to do backslash for certain characters. While in this HTML text, you can just do everything direct. So this method using the HTML text might be better for outputs like code, right? So to me, it makes no much difference between both methods. Most people use the chain of thought with JSON format because that's what has been used typically, even for OpenAI. But I think these HTML tags are okay also. All right. So the RL training, after you do RL training for DeepSeek, you realize that the average length of response for the model increases as you train more. And that's not surprising, okay, because you ask the model to think, right? So, so there's thinking tokens added to the out. So the more you think, the lengthier your response. And that's also why in the paper, they actually mentioned that for short queries like hello, they basically don't do this chain of thought process. They actually curate the SFT data set to make sure that for short and easy questions, it's more straightforward without the chain of thought. Okay, but for complicated questions, people have found out that actually the more you think, the higher the chance of getting the answer. And the interesting phenomena that was found out is that there's this thing called wait that is used by the model to signal that, hey, I need to reflect more or I need to correct my answer. You see a lot of the DeepSeek-R1 responses, they put wait, or wait something. And in fact, some researchers have also shown that, if you take the LM output and you just add wait at the end of the generation and you force it to generate more, it can actually solve harder and harder math problems. Yeah, so there's something unique about this way to signal the next generation. And over here, you can see this is what the model learned by itself through the reinforcement learning process. Basically, after you ask it to generate chain of thought, and then you basically put this whole thing inside your SFT data set, you realize that more and more responses start to signal this wait. Okay, so this is cool because this is a learned response based on the objective to get correct answers. Apparently, this tokens of wait helps like in reflection. Okay, so now we move on to how the model is trained. So there are 3 steps. First step is the cold start. Second is the reinforcement learning. And third step is the repetition of the whole process by distillation to the next model. So let's see how this is done. So first phase is cold start. So one big thing that they did was they constructed a small amount of chain of thought data to fine-tune the model. Okay, so what this means is that, if we want good trajectories, we need to have a good starting point. Right? This kind of reminds me of, when you have AlphaGo, they actually train it on expert data before doing the RL process. Okay, of course, there's also AlphaGo Zero, where, there's is learn from scratch without expert data. Okay, but it's really, really much harder to do this. And actually, AlphaGo Zero is not really tested with humans. The humans one normally is AlphaGo. This is usually done in the computer playground. So we don't know for sure whether learning from scratch would really be like good enough. One thing for sure is that if you have a good starting point, it's much easier to do RL on that starting point because your policy is already biased to something good. So how they did this is they just take train data, train output from like good LMs, maybe from O1, and you just collect some data with the reasoning responses and so on, and use it to train the model using a fine-tuning process. So the question is, how much of this performance actually came from other models, right? Because if you have a good starting point, you win half the battle already, right? So can this RL process learn from scratch? Okay, this is a question that we need to ask ourselves. Okay, can we actually learn this RL process from scratch? I think it's very difficult actually, because there's so many tokens that can be output. How are you sure that the tokens you output are correct? I mean, it would be, especially if your answer is in the thousands of tokens, you will really need a very, very lucky sequence in order to get your answer. So if you ask me, I think it's almost impossible for this kind of RL methods to just sample trajectories and reinforce good ones to work from scratch. It's really difficult. You have to start somewhere.
Sorry, just to interject a bit.
Yeah.
Then, but isn't it also has a very exponentially large search space? It's the same problem, right? But it works for Go.
Mm, yes. So for Go, actually, is easier than this. So basically, what happens is that you need to like do some form of search in order to get the answer. And for Go, the search they use is like Monte Carlo tree search. And even then, the state space that they search in for the Go bot is much smaller than the token space that we have here. So, I mean, yes, you can do it from zero, from scratch, but you need to have some efficient search method. And
Right.
It's quite difficult for LM token outputs.
But if I remember correctly, there's one analogy where it says that the search space, the number of possible moves in Go is more than the total number of items in the universe, right? So the part that reduce the search is the Monte Carlo tree search, right?
Yes, Monte Carlo tree search is an algorithm to go through like the various paths. I mean, you can also do that for LMs. You have certain start node, and then you sample your next node, and then you sample your next node again, subject to certain criteria, which is like the exploit trade-off, which means that you choose a node based on like how often you have explored it. If you haven't explored it, you go there, and if the node does well, you exploit more. So you can do that. There's some problem with this Monte Carlo tree search method though. I mean, I've done work on AlphaGo Zero, and the problem is if your initial value estimate is wrong. Let's say you bias this node as a value of 10 compared to the other node here as a value of 1. And somehow this value is actually wrong, right? Because you estimate wrongly. You will actually spend a lot of your time traversing the wrong part of the tree. And this is the problem with Monte Carlo tree search when you have rewards that are not really like you need a long time to get your reward, you might face this problem. For Go, you face this problem also. That's why I think AlphaGo Zero, you might need to bias it a certain way. If not, it might not learn the right trajectories. Especially if you're learning through self-play, it might reinforce the wrong sequence of moves. So I think in terms of like tree search that uses intermediate values or like estimated values, they always have this problem that you might bias the search wrongly. So yes, you can reduce the search space with Monte Carlo tree search, but if your value estimates are wrong, you might be in a worse state because you search the wrong parts of the tree.
But that's not even in their paper. That's not even the reason they abandoned MCTS, right?
Actually, they mentioned that because it's very hard to get an accurate intermediate value
Oh, really? I thought it's due to this method is very time consuming.
and also time consuming, yes. But the main reason I think is because the intermediate value estimates may be wrong.
Okay, I'll check again.
Yeah, it's one of the sections under
Okay,
fit
okay, okay.
methods.
Actually, come back to my main point. I sidetracked a little bit, but my main point is like I agree with you. It's hard to use um pure wait, not pure. Like it's hard to do it in the AlphaGo zero fashion to train language model. But I think it's for a different reason. Because in AlphaGo zero, you are playing a game, a zero sum game, right? You are playing. You are using two different versions of the same agent against each other, but in this setup, in the language setup, there's no clear definition of such game. It's like just a different setting, right?
Mm, I mean, in this case, the game is a single player game.
Yeah.
You want to maximize your score.
Mm-hmm.
Yeah, it's not a two-player setting like AlphaGo. But the way you train it is similar. I mean, if you use Monte Carlo tree search, you search, you give a value, and then you bias your search again, and so on. Yeah. So I think there's I mean Monte Carlo tree search you can reduce the search space, but you might reduce it wrongly. The point still holds, even for single player games.
Yeah. Okay. I'm just saying there are more issue in this setup if you want to use without any prior knowledge. Also, but actually, okay, we can discuss that later. So I have more comments on that.
Okay, cool. The rest, any other things you want to add before we move on? So I think this GRPO part is conditioned on conditional on whether you can even generate the good trajectories in the first place. So I think this cold start is actually very important. So Matt, you asked something. So the reason OpenAI doesn't show the thinking steps is because it can be used to train other models. Definitely. If you take the entire thinking step from O1, you can train a model almost as good as O1 just by sampling it over a various diversity of topics and getting the answer and you fine tune it. Yeah, it's very possible. I mean, you can do it for O3 now since they released the thinking tokens, I think. Yeah. Yeah, that's exactly the reason why OpenAI didn't want to release the thinking tokens. All right, so let's move on. So the RL phase, they call it reasoning oriented RL, basically means answer oriented RL. So basically, they train it on things with a very, very clear answer, maths, logical reasoning with clear solutions. Okay, I emphasize again, clear, unbiased solutions. And this is very important because just now we are talking about the Monte Carlo tree search and how your values, if you estimate wrongly in the middle, you might lead to horrible outcomes because you focus your search on the wrong parts of the tree. Here, if you have very ambiguous questions, you might actually get a wrong value and you reinforce the wrong trajectories. And that's bad because in general, when you reinforce wrong trajectories, that can lead to downstream effects where you solve other similar problems in the wrong way as well. So in order to make our reasoning model good, we want to make sure that these trajectories are of a good and like more or less an assured trajectory. Okay, so you use problems with clear solutions. And also that's why like O1, O3, you see the benchmarks they use, they're all benchmarks that are unambiguous. Okay, they have clear answers. GPQA, AIME, Frontier Math, all these have clear, unbiased solutions. Okay, you definitely have a solution. And yeah, so we basically use this kind of data sets and what they realize is because of the training data they use, the chain of thought that is generated by like asking the model to think might contain more than one language. So this is quite curious because I think maybe they use quite a lot of data sets in Chinese compared to OpenAI. So sometimes the thinking process they might think in Chinese. And this it's actually not a big problem to me because as long as the answer is correct, I don't really care how you do the reasoning, right? But they think that this is an issue because like it affects human readability. So they also incorporate a language consistency reward during the RL training to bias the model to output all in the same language, right? So the final accuracy of the answer based on the verifier plus this reward for language consistency forms the total reward. And then we do the GRPO process we saw earlier to reinforce the trajectories that are better and and basically de-reinforce those trajectories that are bad. And essentially this is the crux of DeepSeek R1. So as what I said earlier, if we were to end on one slide, I'll end on the GRPO slide because that's essentially what R1 is. Okay, so after we do this phase of RL, this is the other ingenious phase. This is a phase whereby we don't end, all right, we don't end on the RL training. We instead take the RL training, take the resulting checkpoint, collect more data for the next round. And this is so cool. This is so cool. I must emphasize that this is an incredible idea. Why? Because there's some limits to reinforcement learning. When your model is like maybe your model has reached. Okay, let me just draw this diagram out. All right. So let's say this is the best outcome. All right. Okay, over here the x and y axis are arbitrary. I just want to demonstrate like how this might help the process. Initially, your model starts here, and maybe through RL you might bias it wrongly. You bias it until here. Okay, what happens is that after you take the supervised fine-tuning data set, you have certain categories you want to test. You might get some data that brings it to here. Okay, the fine-tuned model might bring it here because instead of just being overly biased to one domain, maybe I do some data for a diverse domain, you might bring the model somewhere here. And then when you do your RL trajectory, again, you might bias wrongly. Okay, maybe I show you bias somewhere else now. You might bias it somewhere else now. You might bias it to somewhere here. You might bias it here now. Because again, the RL process is not uh it may not be the most competent because you just look at answers, your reasoning might be wrong and so on. But again, when you collect this fine-tuning data, you do some filtering, what happens is that you maybe you get something closer to here. And then you can do the RL process again, and eventually, hopefully, you reach your intended point here. So this is your SFT data. SFT data distilled from the RL model. Because I've done RL for 4 years in my PhD, and I can tell you that RL is very unstable. To learn from a reward is like trying to chase something that keeps changing direction. Yeah, that's why later you see the next part of the slides, I actually advocate more for goal-directed learning than reward-based learning. Because like this kind of rewards from the environment, it can be so sparse. It can be very hard to even learn from such rewards. You might even go off track. Like maybe if your first trajectory gets you the answer, like for example, what is 1 plus 1? Your first trajectory say mix helium and hydrogen, and that's why you get 2. Therefore, answer is 2. So the rest of your math questions, maybe you talk about helium and hydrogen, but that's totally wrong. So RL doesn't really care about this because RL just looks at the final reward, the final answer. And you can see that, your trajectory might really go out. Okay, but with SFT, with some filtering, okay, and I emphasize about the filtering part, this filtering is also genius because papers have shown that, if you just take experiences from other agents and you filter them, or you take data sets and you filter them, like if you look at some paper like 5.3, tiny stories, this shows that a highly filtered data set with only good data helps a lot. So small models, but with very, very good data helps a lot. So this filtering process helps to take what is chaotic in the RL model, all right, and filters them to clean, clear responses that are more possibly correct, right? This makes the model get better on track to reaching this holy grail here, which is the the best model we want. All right. So this phase is important. Actually, it's really important. If there's a second slide for today, this was the second slide. This is really important because if we just use RL natively, I don't think they will reach the performance that they reach. So this rejection sampling part and starting from the base model with better data, that's really a very important step because you can take away all the chaotic stuff that RL might imbue in your model and just focus on the SFT based on certain known categories that you want, right? So you can ground the model again on a clean start state. So really, really cool. And you do this many, many times. I don't know how many times they did it, but I'm quite sure they did it many, many times until the model cannot improve anymore. Yeah. Okay. Questions on this? I think this is an
Yeah, yeah,
important.
I have the
Yeah.
questions here. Yeah. Actually, more than one. I have one.
Oh,
Okay,
go ahead. Go ahead. Yeah.
first one clarification to make. So, I think it's important to distinguish. Like, I think there's two separate reasons that RL may not work as good as well as one would expect. One is you just mentioned about the sparse reward problem, which is different from another problem you mentioned like earlier, which is it's hard to train a good value network to estimate the value, right? These are two different problems, right?
Okay.
No, I'm just clarifying. These are two different problems, right?
Uh, so the sparse reward is basically you don't get a reward. Yes, that's
Yeah,
one problem. The
yeah,
second problem is you estimate the value wrongly. Yes, that's another
yes.
problem. Yeah.
And their GRPO actually fixed the second problem because they do not require additional. They do not estimate in their advantage. They do not estimate V, right?
So the GRPO is not the one that makes the value estimate correct. They use a verifier that is
No,
based
they do
on.
not. In their advantage definition you showed just now, they do not even have a value term, right?
There's this reward term. This reward term is actually estimated by the verifier. So
Yeah, but the reward is different from because traditionally RL advantage defined as Q minus V, right?
okay, so in this case, there's no ground truth value here.
Because like
There's no critic
estimating
here. There's no
V
critic.
or
Yeah.
Q is different, is the different thing from estimating R. So here the R is given by the checker, right? The because it's verifiable. So
Yes, yes. R is given by the
R is
verifier.
well defined, but
It's actually the R here is actually both the verifier plus the language consistency reward.
yeah. Anyway, this is well defined. Just like in chess, but at the end of the round, whether you win or lose is well defined. But the hard part is to train a good value network to estimate the advantage during the play, right? Before reach the end. So my point is, I think this method initially, I feel like GRPO the main advantage is to get rid of the value head, which is because they have a lot of constraint on the compute. But now I realize actually another good thing is they do not need to estimate the value. They do not need to have a value. By getting rid of the value head, they actually make it much simpler because it won't have the problem you mentioned. You will bias the value if it's not trained properly, will bias, and if it's not good.
Yes, yes. There's one
uh,
less bootstrap. So there's because in traditional policy optimization, there's a critic. So the critic might be trained wrongly also. So in this case, they take away the critic. So that is an improvement, I think. Yeah, because the critic, there's no more bias that you can face when your critic is trained wrongly because there's no more critic. Instead, what you do is you take the verifier score directly, which is
yeah,
more assured. Yeah, you're right.
it's like a one stone, two birds kind of
That's
strategy.
right. That's right.
Yeah, very cool. And okay, then come back to the just now the slide.
Okay.
So now is a question. So you are saying okay, because I try to understand their pipeline, the flow chart, right? I feel I'm not sure if I understand correctly because it looks a bit complicated to me. So you are saying they do this RL, reasoning RL, then SFT, then reasoning RL like quite a few times.
Yes, yes.
Oh,
SFT will be used to train DeepSeek V3 again, but the DeepSeek R1 is based on the V3 as the base,
oh, I see. So they are using RL not just to train the reasoning model, but also to further improve, bootstrap their
the base
base
model.
model.
Yes.
Oh, I see. Okay.
Yeah, so all this SFT data will go to the base model.
Then they are using the updated base model to
Yes, for
do
the next
another round.
cycle.
I see. Okay. Okay.
Yeah, so you're right here. This paper that uses GRPO, they help to solve one of the bootstrap issues for the critic by using reward that is based on actual verifiers,
Yeah.
which is awesome. I like
Because
this
I,
idea.
I, I watched another talk. Actually, they had tried to replace PPO with GRPO. And they say just this simple replacement get them like a 1.5x or 2x improvement. Just this very simple change.
It's
Everything else
possible.
remains
Yeah.
the same. So that made me like I was very surprised because initially, as I said, like I thought it's just a trick to make use of the limited compute, but turns out
GRPO is a
it's
very awesome
uh,
idea because it uses group competition to improve the model. So I think in human society, we do that all the time. When you submit papers, the reviewers will look at all different papers and then they will judge you on a relative scale. Then maybe those papers that score above 7, they'll get in. Those below 7, they won't. And then people learn from the papers that get in and then they improve the style and so on. So in some sense, like even for research, for industry, we all learn from one another. Let's say DeepSeek here has a breakthrough. We all learn from DeepSeek and then we improve because like maybe an external verifier has given it a high score, which means the benchmark has given it a high score. We learn from it. Yeah, so actually I would really love to learn from like OpenAI, Gemini, and so on, but they don't release it open source anymore for their methodology and so on. So this is basically how human society also learns as a group. Like we compete with one another, we learn from the best. And uh, the back to GRPO, the beauty of this is that you don't learn the same thing from everyone. You learn based on the proportion, based on the percentage improvement that you have over the group average. So I learn more from some model or someone that is significantly better than the rest compared to someone that is just a little bit more. So I like this idea because you can really just, you know, prioritize who you learn from. And yeah, this is really cool to me.
okay. One last short comment is you mentioned the sparse reward problem of RL. I think in the paper they also tried to add intermediate like you kind of reward shaping, right? To add what they call the process reward model. Like they're just trying to give assign. I think we discussed it last time as well. They were assigning this reward for individual steps, but turns out it's not even as good as the pure RL. Yeah, for some reason.
Yes, I will cover that later. There's a slide on it. So basically, the process reward model is not as good because the process rewards are hard to measure, hard to train. As it's really hard to know, like if you're doing a math question, it's really hard to know in the middle whether you get the answer or not because you still need the remaining steps to decide.
Okay, that's all.
Okay, good. I like the discussion. Anyone else has anything to add?
I mean, I
Okay.
had a sorry.
Oh, hi, Derek. Yeah, please go ahead.
Yeah, no, I had a question from earlier. It was a reference to the GRPO. If you want to go back to the slide, there
Oh,
was
yeah,
that
sure, sure.
form. It was that formula that was doing the averaging of all the responses, and then it also does the formula at the bottom to find the highest value ones. Is that applied after the cold start for the RL, or is the cold start part of that formula?
Okay, so the cold start has already happened because you have an initial policy here, which is based on the supervised fine-tuned model. Means the cold start is already incorporated in your original policy. Then you do RL on that policy after the cold start.
Okay, got it. Okay, yeah. And that's running on both the fine-tuned model and the base model, or are they both
Uh,
improving at the same time during the iterative bootstrap?
yeah. So like DeepSeek V3 is the base model. Then after that, you have DeepSeek R1, which is the RL after RL model. So essentially, after that, you generate the SFT data, you train the base model. So I don't know how you want to call the models after you train with SFT because maybe you call it DeepSeek V3 version 1, version 2, version 3, version 4, but they didn't put those things there. It's just DeepSeek V3. So it's a bit hard to, distinguish the base model versus base plus more SFT data.
Got it. So it's a pipeline that loops into itself. So the V3 is constantly improving and feeding better and better chain of thought trajectories for the R1 model.
Yes.
And then the R1 model can then do the SFT to feed back into itself and repeat. Okay. Yeah, I get
Right.
it now. So it's
But
not the same. Yeah,
the
go ahead.
cold start data is different. Cold start data doesn't come from the RL model. Cold start data comes from other models, perhaps from O1. Okay, so of
Right,
course
right.
we don't know where it came from, but likely it's from O1.
Gotcha. Yeah, so it's the distillation, and then you run the iterative bootstrapping afterwards.
Yes, correct.
And you run through the advantage and the averaging. Okay, that makes more sense. Sorry for
Yeah.
missing that. Appreciate it.
Hey, no worries. And that's why I say, like, if without this cold start data, I don't really think this RL process would work because there's just so many token space to traverse to find the answer. How are you sure whether you get an answer that actually hits the mark? Like certain questions that we have, like Olympiad questions, you need like 10 steps to solve the answer. And without the cold start, I highly doubt any model can just hit those 10 steps just by sampling. I mean, Arc Challenge is similar also. Like, people try to sample, like Ryan Greenwood. He tried to sample the Arc Challenge, and then he found that, oh, you can get up to 50% solve rate on the test set. I think those kind of things happen only when your model itself already contains some form of answer there. If your model itself doesn't really have the trajectories, I don't think just sampling would solve it. Yeah.
Sorry, but O1 does not give you reasoning traces, so how does it help to become co-star data?
I mean, you can ask the answer to include the reason also.
I don't think that works.
I mean, you would know until you. They probably use some way to extract out some reasoning. I mean, if your answer, you ask it to output in JSON format thoughts and answer, I'm sure the thoughts will come out also.
If that's so simple, then their GRPO wouldn't work, right?
Maybe they use this prompt also to O1. Like we can try this one, copy paste into O1, see whether the thing comes out or not. Yeah. So if let's say in the answer that O1 provides, not the reasoning token, the answer there's a think steps also, then you might elicit some reasoning from the O1 model. Okay. By the way, the main point here is not to jailbreak O1 or what. I don't really care about that. I care more about how this process of reinforcement learning with this GRPO works. So that's the main point for today. Okay, due to the lack of time, I shall move on. And now I move on to the food for thought section, well, which includes some of my insights and also some of the insights that the paper has shared. Let's take a look. So this is my insight. So basically, I feel like in order for this reinforcement process to work, we need to sample diversely. We need to have enough trajectories such that the good ones come out. And how can we sample this from the model itself? I think it's very difficult. That's why there's cold start data. I also think there's another way to cook some behavior out. So, you can ask it to answer in the following format. So maybe like, ask it to think about thoughts about A, thoughts about B, use both thoughts to answer. Yeah, so if you already know like certain pipelines, like I don't know, or chemistry question, maybe you need to first break down into small compounds or small elements. You maybe ask it to think about what elements could it be made of. Then you think about, is this an exothermic or endothermic reaction? Some stuff like that are domain knowledge. If you already have certain domain knowledge here, you can put that into a structured pipeline for chain of thought. And this could actually help to elicit better thoughts compared to just saying that, hey, output in this thoughts answer. It's too vague. Like the most vague one is let's take step by step. I offer absolutely no help at all. I just ask you to think step by step. So this is the most vague. This very vague, hard to elicit correct stuff. So these two are very vague. This one is let's take step by step paper. This one is DeepSeek R1. So I think just this thoughts answer is very generic, very, very generic, but may not get the answer. Whereas if you have a certain domain here, it's more specific. If you do it, higher chance of getting the answer. The reason why I'm so confident to say this is because for the ARC challenge, I use some method like this. I ask it to think in grid form, pixel form, what else? Grid view, object view. Yeah, ask it to think in 3 different views. The answer has significantly improved compared to just asking it to think about thoughts and answer. So I'm very, very sure that having a very structured pipeline for thoughts is important. So maybe this is one way to get better trajectories. Of course, the other way is you do some form of search over token space, but it's really difficult because there are many tokens, more than gold positions, gold bot positions.
This is an open thought about this process, but would there be an advantage to, because we're doing iterative bootstrapping, so this is actually really useful for that, like do role playing or role-based prompting during the iteration process. So you can start initially with prompting it to play the role of a mathematician, or very like you try to hyper specify the role it's playing so you constrain its output to a certain degree of like bias, and then you run the iteration on it and self-improvement. It can get to a certain level of accuracy and of reasoning. Then from there, try to see if you have that leftover training to be used for more broad questions, and test that out and see if it brings over the role-playing reasoning as an integration of its tokenization process and its token reasoning, and its larger reasoning when it's given harder questions or more abstract questions, when it's doing the bootstrapping between the base model and the refinement, the RL.
Yeah, I like this approach. So basically, instead of having one model, you have different models, or maybe it can be the same model, just prompted differently. And
I'm thinking so. If you have enough parameters, you should be able to fit the nuance into there and keep that role playing training early in an earlier step and have it carry over to the later steps and see if it'll improve the learning rate or improve the reasoning tokens and improve the reasoning traces.
Indeed. So I think in the future plans that I have for AgentJo also, like in order to get different outputs and consolidate the good ones, we need different kinds of agents. And you can use the role-playing method that you talked about earlier, or we can just condition it with different contexts. And yes, from there you can get various diverse samples just by constraining or just by biasing the output for each agent to a certain context. And I think this is some room for improvement. I'm sure some people are already doing experiments on it right now. The issue with constraining this context is that although you have a higher chance of getting the answer, you also don't have, it's not general. So this kind of approaches are not very general. And I think it's good if we want to just sample the right answer for a known domain. But if you want to do general intelligence, I think this may not get that. I mean, the role playing method you talked about earlier may be general because you can just say a very general role. Yeah. So I think there's some room for exploration here. The key thing I want to highlight is that getting the right trajectory is hard. And so any approach that helps to increase diversity is useful. All right. Yeah, Derek, you want to say something?
Yeah, I did because I was thinking about it. For the generalization issue or the hyper specific issue, it might be you might be able to do your idea of multiple models then, because the advantage would be that you'd have multiple models, each with their own hyper bias, but they have very high accuracy with very efficient reasoning traces, very accurate reasoning traces, and maybe you can use your iterative process for the hyper models, hyper specific models, as a distillation for later models. So you might be able to do hyper specific models that are hyper fine tuned with the reasoning bootstrapping process, get those really good reasoning traces from them, and use those models as distillation for fresh models. Again, have a fresh model, but it has all the previous reasoning traces distilled into it from the fine-tuned models that are doing the role system, and have that distillation feed into the new model so that it just takes all of the good reasoning traces, but doesn't fall into the biasing issue because it's not getting hyper prompted with hyper specific biasing. It's just taking really good distillations from all of the hyper specific models from earlier as the distillation. I don't know,
Yeah.
that would be my approach.
You can do multiple agents, multiple models with different fine-tuning approaches, definitely. So I think this is a possibility, and there's really a lot of possibilities to do this. The main thing I just want to say here, because I want to move on to the next slide. The main thing I want to say here is we need a very diverse sampling method if we want to get this RL process working. In fact, it may not even be RL process. Later, let's explore, right? It can just be filtering the right trajectories to train, right? So you start to see a common thread here, right? Like you need the right trajectories to sample so that you can reinforce the correct ones. But must we do reinforcement learning? That's the question, all right? Is RL really needed? Oh, just nice. Okay, exactly my thoughts indeed. So if RL really needed, all right, just take a look at this Quen model. And basically this Quen model is the base Quen model. It's not very good with any of this. Okay, actually it's quite good for math, 90% already. All right. So with
Oh,
RL,
no, that's not the base.
oh, this,
That's a reasoning model.
oh, okay, this has already been trained
That's
on
why
reasoning.
it's good.
Okay, yeah. Okay, thanks for the clarification. Sorry. So this basically after you do the RL process described in the paper where you take multiple trajectories, do GRPO to reinforce the good ones, de-reinforce the bad ones. It does have some improvement. Like, but if you take a look here, can you see something that I see? Can you see that it's not exactly that great, right? Like like some of the after you R1 it, can you see that the score, some of them went down? Yeah, so then they also tried a distilled method where you take the Quen model and then you just distill it with the DeepSeek R1 outputs. And look at that, look at the improvements. It's like 20 percentage points, 4 percentage points, 8 percentage points. Can you see the big difference between the distilled model versus the RL model, RL on by itself? So you see, RL is not as good as distillation from a bigger model. This proves it. You see, RL is not good if you cannot sample the right trajectories. In fact, the RL actually reinforced the wrong stuff. Look at this. The pass at one actually dropped from 50 to 47. Yeah, they did not highlight this in the paper at all, but wow, R1 using the RL method dropped the performance for a smaller model. So like if you don't bootstrap the data well, like RL process might just go haywire and just reinforce the wrong stuff. I mean, when all reward traces are equally bad, you know, you might just reinforce like everything. Okay, actually, when all are equally bad, you reinforce nothing because your group average is 0. All right, so but if you don't have even a good trajectory to sample from, you can see you can't really improve. Okay, whereas if you just distill from a good model with good trajectories, you can improve because of course this model is better. It has better trajectories to give you to learn. So there's a very interesting point here. Can we just select the right trajectories to fine tune on? Because it looks like the SFT process is more important than RL here because like we actually bootstrap a better model with SFT. Uh, can we just select the right trajectories to fine tune on? And can that replace RL totally? So the pipeline imagine is like this. Sample G trajectories, select maybe top X trajectories, and then fine tune filter to make sure trajectories are good, and then fine tune on base model. So this is step 1, step 2, step 3. Can this be good enough? Of course, GRPO, you actually train your model weights, you bias your model weights training in terms of how well it is relative to the group average. But I'm just thinking, can we just select the top X trajectories and that's good enough? I mean, if we want to do some bias to learn more from good trajectories versus good, okay, from excellent trajectories versus good, we can just put more of the excellent trajectories in SFT dataset. So basically, you can increase the proportion of your excellent trajectories by like repeating it 5 times compared to good trajectory just 1 time. I mean, it's essentially the same thing as you increase your weight update, right? Because you do it more times. right? I'm just thinking whether you can just use a method like this and we do away with GRPO totally. Okay, the GRPO, the concept is really just group competition, learn from the best. Okay, and of course, there's also another thing to de-reinforce the lousy ones. But you know, if you SFT the good ones, you are also de-reinforcing the bad trajectories also. So food for thought, because I don't have the answer for this. But I'm just thinking, you know, is actually the RL process too unstable to use? Can we just use SFT? Can we just sample the trajectories, go through some filter to select the best ones, and just train on the good ones?
So
Okay.
can I share my take on this?
Yes, sorry, go ahead.
So I feel like my understanding now is like the RL, whatever you can get from RL is like an upper bound of whatever you can get from SFT, because SFT is basically a issue of imitation learning versus RL. Or if you like put it in a more colloquial term, it's like system 1 versus 2, right? You can the way I understand it, SFT is system 1 learning, and RL is system 2, because RL is like you are using a lot of compute trying to figure out what are the
That's RL with Monte Carlo tree search or some tree search. In this case, the RL used in DeepSeek-R1
I'm just
doesn't
talking
have any
RL.
tree
I'm
search.
saying RL in the sense of trial and error.
There's no try and error
Error.
version for DeepSeek-R1.
And so and SFT, you don't try and error, you just learn from the best. If we assume that you can find, like, you already know which trajectory is the best. The problem is you do not know, right? Like, or maybe like if your model, you fix your model weights or policy, maybe then it's very limited. Like maybe the optimal trajectory you cannot successfully sample with your current model weights. Then you have to somehow fine tune or modify your current weights to get a better trajectory. So that, I think that's what RL is doing. So it's like, that's why I'm saying it's like an upper bound of SFT. Here the result also shows that, right? Because you are the third result, it shows the result is distilled from R1. That's why you get a better result. You doing RL from scratch on a smaller model, which is not cost efficient. That's because we already have R1. If you don't have R1, you cannot do this
That's
process.
right. That's right.
Yeah. So you still need someone to push the boundary of the best reasoning model through
Correct.
RL. Then the rest you can just very simply learn through distillation or SFT from that model.
What if I told you that no, you can actually do your learning by just sampling and filtering, and then just fine tune again, then you can learn again.
But as I said, I think that probably wouldn't work, because maybe the best trajectory for your current model is simply not good enough. So the optimal trajectory is so hidden in your sampling that it's a very low probability you are never able to sample that out.
Actually, there's some validity to that. Like the RL process might bias your token probabilities much more than SFT can. So RL might still be needed to bias it, but because after you bias it, it becomes a little unstable. You might want to retrain again.
The unstable part, yes, that's why the order to make it work, they need a lot of engineering work to make it work, right? But once, if you can overcome that part, then you can push the upper bound of the performance. And SFT is like, basically SFT is like, because the model is so good at learning, if you know what is the best to learn, then you can just apply SFT. The problem is most of the time you do not know, if it is, especially for this kind of open-ended reasoning domain.
Okay, I mean both views are valid. Your view and my view are valid. I think the idea is just to keep improving model by biasing token probabilities to better trajectories. Essentially both methods do the same thing. It's just how you do it. So if you use RL, you do it by the policy improvement. If you use SFT, you do it by fine-tuning, which changes the model token probabilities as well. So
Yeah. But you
yeah.
see, just now you mentioned a pipeline, they RL then do SFT, right? They do this a few run. So if that works, why not just SFT train it on its own data?
Yeah,
Then
that's exactly my question. Can we just do SFT? I think we can. Maybe I can run an experiment to find out. I do think this might actually be good enough. My gut feel tells me it can. I don't have the evidence to back it. Yeah.
Okay.
Okay, yeah, I mean, we can discuss more after that. I still have some slides to cover before we do discussion. Derek, you want to say something? I saw your mic down a bit.
No, I did. It was just back to Jong's point. He was talking about the upper bound limit, and I was contemplating to myself that he used the analogy the system 1 and 2, but for me, the system 1 in this context is the whole neural network already. So if you're running your reinforcement or whatever process you're using to keep getting better and better trajectories from the original data set or the original trajectories, so it abstracts from it, ideally you would want system 2 to do the hard math or the hard memory, so that it can come up with those trajectories and within that search space much more slowly and more computationally expensively, right? Because that's the problem with most symbolic architectures is the search space problem and the computation problem. But ideally, what you would want is that you would want some kind of symbolic or hard code system that can be your system 2 that can run that and run those really hard search space problems and algorithms that are very expensive to run, then use the small amount of very high quality trajectories you get from that, from running those, and use that for your fine tuning, whether it be SFT, RL, whatever you think works best. What really matters at the end of the day is the trajectories themselves that you tune on with whatever technique you want. So as long as you have a method of improving your trajectories and pushing your trajectories to the next level, you will always be able to improve your neural network to that next level, because the neural network can abstract from the trajectories and model itself around those trajectories that are more accurate or more high quality.
Yeah, indeed, that's exactly the point that I try to make. Like, it doesn't really matter what method you use as long as you get better trajectories. Yeah. Okay, cool. Shall we move on? Yep, let's go. So the key insight that they have in this paper is also that, people always talk about, process reward models trying to like learn intermediate values. And they realize that they have tried with this and they realize that it doesn't really work because it's very hard to define a fine-grained step in general reasoning. Like, how do you know whether just adding one more assumption can solve the problem compared to not having that? It's very hard to tell in the middle. Hard to determine whether it's correct, right? And it can lead to reward hacking in some sense that sometimes you might reinforce certain intermediate steps to get your get your answer, but this reinforcement of these intermediate steps may not work in all cases. So these intermediate rewards have a lot of problem, and they also mentioned that like Monte Carlo tree search didn't really work because they couldn't use these intermediate rewards to bias the search well. So they tried both Monte Carlo tree search and process reward models, and eventually they came to the conclusion that they cannot use either one. So I think this is similar to if you look at O1 and O3, also don't really use MCTS. At least that's what some of the researchers there claim. I'm not sure whether they use process reward model. Maybe they use a reward model only for end trajectory, not intermediate. So I don't know. If they use a reward model, it must be for certain situations only. Because if you look at the benchmarks they use, most of them are objective benchmarks. You don't really need to train a reward model for that. Right? You just need to look at the answer and you can get the answer. You can see whether the trajectory might be correct or not. Okay, so that's all for process reward models. So I just want to touch on some of the insights I have. So this is from me. Like, why can't we learn more from goal-directed learning rather than from reward-based learning? So if you look here, this is a mouse. I always like to use this slide, all right? The mouse transits a maze from orange to purple. So when it's transiting, its mind is doing some hippocampal replay. It goes from orange to green and then green back to orange here again. And a lot of traditional views says that this is to, impart the reward from this point back to this point. And also like it actually thinks ahead of time and, plans its trajectory again. So you can also view it as reward-based impartation, but I view it as goal-based impartation. So it's, for example, like given a state and a goal. Like for example, if let's say this point is A, this point is B, and this point is C. Given that we know A, B, C is my trajectory, I know that I can go from A to B already. I know I can go from A to C. I know I can go from B to C. So essentially, just from experiencing one trajectory like that, I know that, okay, to go from A to B, maybe I take action 1. And to go from B to C, I need to take action 2. And just by doing this, like sampling from different start and end points, which I believe might be facilitated by this, you can actually get a lot of experience just from one trajectory. And I'm just thinking, why not do that for LM training? Okay, so this is whatever you're gonna see in the next few slides is entirely from me, nothing to do with DeepSeek-R1. So why not we just do goal-directed fine-tuning? What do I mean? Okay, I illustrated this with an example. Last time I drew it out. Now I have a proper slide for this. So let's say my prompt is like that. Calculate 1 plus 2 plus 3. And then my completion would be like the chain of thought needed to get here. Why not we, instead of just training from this question alone, we can train with this question with maybe the first step. And then we train the next completion. And then you train with the second step also, and then you try to train for the completion. So essentially what happens is that I get to understand how to get from my start state, which is more and more encompassing, to my end state. And I mean, in some sense, this might already have been done in the LM fine-tuning, because in LM fine-tuning or training, we may be already using some sliding window. So, maybe this is already done. It's just that, we could be a bit more explicit in how we do which is the start state and which is the completion. Yeah, so the advantage of doing that is that given a certain start state with certain already predefined steps, I already know how to get to my endpoint, like in more diverse ways. Like, so even if this intermediate step might be wrong, if let's say this step is wrong, then I would know how to, correct it. Because if let's say the rest of the trajectory is to do correction, then I know how to correct this step. So this can also be used in agentic workflow training, where you train the agent based on like your goal and then your actions that the agent already done and like what's the next few actions to do. So something like this, I'm not sure whether this is already done, but I would say there's quite a lot of promise here, because you can learn from a lot of diverse start states just by doing this. Okay, next up. Yeah, so you got to say something.
Yeah. So I think this is very similar to you get the reasoning trees, then fine tune on the reasoning trees, right?
Yes, correct. But it's just about where is the fine-tuning beginning. Like, do we have
Yeah, I get it. Usually you just want to fine tune on the end, but now you're fine tune on every single steps.
Yeah, I mean, in some sense, this might already be done, because whenever we fine-tune the next token, we always use the earlier token as the context, right? Let's say you want this token, usually we already use everything here as the context. So I think this might already be done in current training methods.
Yeah, I'm referring to Hugging Face way of doing SFT. Like you explicitly tell the model to fine tune on which specific token. You don't actually fine tune on the entire sequence. Yeah.
Mhm.
But I don't know, maybe they did it in the same way as pre-training, which is fine tune on every single token. I'm not sure.
Yeah. So this may already be done, but this is just the part 1 of the idea. So part 2 is like this. We can change our goals. All right. So instead of, I think this is not done, all right? So instead of saying that, hey, I need to get 1 plus 2 plus 3, let's say we did until 1 plus 2 equals to 3. What I do is I change based on the steps that I have made. I update my question according to the steps. Create a new question based on steps that are already done. So essentially, I don't have to get the right answer. I just need to I just need to reinvent the question. Okay, can you see the benefit of this? By doing this, you actually can make your goal exactly what you encountered in your trajectory. You don't have to get the right answer, all right? Let's say if the answer breaks down at 1 plus 2 equals to 3, I don't have to use 1 plus 2 plus 3 as my main question. I can just put my goal state as 1 plus 2. And whether this is learning or not, yes, it's still learning, because you learn how to get 1 plus 2. So maybe when you encounter a similar question in the future, like 1 plus 2 plus 3, maybe I already know how to do this, and then I can get the next part more easily. So this kind of way of changing the question according to what you actually have done, I think will be quite impactful in training LLMs because you can learn more from various goal states. You don't have to learn only from right answers. You see, right now, even for GRPO, you need the right trajectories. If you use this method, every trajectory is correct. I mean, this is just a way of saying that you can learn from any experience. I think this will be quite impactful. I haven't tried it out, but this is just an idea that I have.
So
Right. So
it sounds like a way to generate more synthetic data for training.
yes, it's getting more synthetic data. Yes, that's correct. Matt, you said I've had the same thoughts. Are you thinking about changing your question to suit the reasoning also? You're talking about that, right? Oh, yes. Okay, you say yes. All right, that's great. Good that you have the same thoughts as me. I think this is something that I would like to see more because I think we shouldn't be relying on reinforcement learning rewards. I spent 4 years, 5 years doing RL and I realized it doesn't scale. All right, doesn't really scale. I have no idea why people are still using RL for LM training. I'm not like a complete downer on RL. I just think that the reward needs some thinking. Like just learning from reward is not as efficient as learning from goals. And LM is a goal-based method. We fine-tune tokens based on context. We should use that to our advantage. This way of predicting the next token based on the context is a form of unsupervised learning or self-supervised learning. It learns way better than reinforcement learning. So why not turn this to our advantage and make the trajectories we experience always be able to fulfill a certain goal? Yep, that maybe can increase the soft rate. Maybe I should do an experiment on this to just try out the fine-tuning. Yeah, that would be quite interesting. Okay, yeah, it's quite late already. Let me just finish. This is the revolutionary one. Okay, so earlier, actually, this is essentially what I talked about in the previous slide. So in the previous slide, oops. In the previous slide, I assumed that you could just break out your question, but what if you cannot? All right, what if you do something wrongly? All right, what if I do 3 + 2 = 5 instead of 3 + 3, right? Answer is 5. So I asked the model to interpret these steps and form a question, which is usually much easier, all right? Given the steps, it's much easier to give the question compared to the question throughout the steps. All right, so redefine the goal state and then train according to this. And you realize that suddenly you have a lot more trajectories to train on. So yeah, this might be something that might help to increase the performance of O1 and O3 even more, or even DeepSeek. I'm just putting this out here in the open so that if anyone wants to try it, let me know whether it works. Okay, this is just an idea I have. Haven't tried it out yet. So quite curious to see whether this works. Okay. And with that, that's all for today. Now we go through some discussion questions, which I hope to take about 5 minutes or more if you want to talk more to cover. All right, so I'll be just going through the answer. If you have anything to add, just say it out or just put in the chat. So first, how much of DeepSeek R1's performance is from distillation? I would say very much a lot. Because, I mean, we look at the Quen model, just using RL itself doesn't really improve much, right? But once you put DeepSeek R1 inside, it improves such a great amount. I'm quite sure that the bootstrap is very important. The cold start data is very important. Next, can we apply the competition method of learning to learn from better trajectories without RL? I think yes. Just SFT, a filtered set of good trajectories. Right, that's what I described earlier. Can we learn from competition if we do not have any ground truth? I think this is a little hard because you have to use a model to estimate the ground truth. So, unless you have a superior model to evaluate as a judge. If not, there will be errors. And essentially, I think if you use an error-based method to give you the reward signal, you might reinforce the wrong trajectories. So in general, I don't think this is a good idea to learn from competition without a ground truth. There should always be some form of ground truth if possible. All right. Yeah, this is the question I wanted to ask you all earlier. Anyone has other comments? Like, do you think we can do this group-based competition approach if there's no ground truth? Any comments for this?
I mean, I've said my thoughts in the past. Like it's doable, but I really don't think it's optimal because even humans, right? Like we compete with each other, but we still have an outside environment that we get really constant feedback from. You know, like when we're children, we're constantly exploring our environment. We're very curious. We love to break things, see what happens, have an underlying understanding of everything from constant experimentation and constant playing with each other. You know, if you don't have any type of environmental feedback, I don't think your learning is going to be either optimal, nor do I think it will be efficient, because I think you're going to do a lot more sampling just to reach some kind of minima or some kind of truth deep down. I just think that environmental feedback helps to really accelerate the learning process. It helps you to conform to your environment much more effectively.
Yeah, thanks. Exactly my thoughts indeed. So, but if you really do need to learn without the ground truth, then I think just using LM as a judge or like some form of rule-based methods as a judge to see whether the syntax is correct might be okay, but definitely not ideal. Yeah.
Sorry, how do you define ground truth here?
Like you have a fixed answer.
Then I can think of one case where there's no clear defined best strategy, but the result of the experiment is still quite interesting. Not sure if you still remember, there's a very early work from OpenAI. They're doing RL in a hide and seek environment.
Yes.
Yeah. Do you think there's a ground truth in that environment?
The ground truth is the reward that you earn when you win the game. Yeah, so that's the ground truth.
I see.
I mean, of course, there's no fixed trajectory to get there. It's just about uh winning. Yeah, so I guess the win and lose model is sort of the ground truth for your actions, right? Because if your actions are good, then you will likely win. Yeah.
But I agree, there's still some kind of environmental feedback, but it's much less well defined, like what strategy is, like there's many things you can do. Right? Yeah.
It's essentially it's a black box. Like the game is a black box, but whatever you do, you still get an output from the black box that either you won or you lost. So it's still a game, and the games are still giving feedback. So you're still having a type of ground truth, but you don't understand your ground truth because it's a black box that you're interacting with.
Okay, then if that's the case, it's very hard for me to imagine the environment where like you have zero feedback from environment. Like how is that?
That's exactly my point. Like even in real
Maybe
life,
the environment might be you need to write an essay, and the rubrics for the essay is very like you won't get the score for the essay. Like there's no score. You just write the essay and that's it. Like
Huh?
but I mean maybe the ground truth will be like whether
Like
you
even you have an author, you the ground truth, you also can get feedback from whether your work is popular or not. That's still some form of
that's
feedback.
true, that's true, that's true.
So
Okay, so
it's
if you
hard
put
for
it
me
that
to
way,
imagine like zero feedback environment.
there will always be some feedback in some way if there's a competition, right? Win or lose. Someone will need to judge you, and that can be your feedback.
so I think the question isn't can we do anything without feedback? I think the question is how much learning can we accomplish? How much trajectory and how much depth of understanding and reasoning can we abstract and collect from the smallest amount of feedback? I think that is the question. I think it's a sparsity question. Like even with reward systems, there's a sparsity issue, and the more efficient your algorithm, the more sparse your rewards can be, and the more efficient your learning can be. And that's something that's very common in the reward modeling field.
Yeah, I agree. So maybe I need to change the question a bit. So I would say like maybe like competition-based rewards, like the hide and seek, maybe are a bit harder to learn from compared to like if you already have the ground truth as in saying that okay, step one must do this, step two must do this, therefore answers this. So different ways of learning. And I think in this case for DeepSeek, most of the questions have the way you can just explicitly put your chain of thought here to learn from the chain of thought. Yeah. I think this is an interesting point to think about. But I mean, I would say that for most cases, if you want to do improvement, you should try to make the rewards as dense as possible. And that includes, being able to learn from the process, being able to learn from the outcome, rather than just the outcome. Yeah, so yeah, I think I'll leave it as that. It's a difficult learning problem if you just only have a binary win-loss outcome. Yeah, so you can still learn from it. It's just hard. I mean, it reminds me of this thing called GANs, generative adversarial networks. The generator only has feedback from the discriminator whether it has fooled it. And this can lead to model collapse because you may not be able to generate something that can fool it. But if, let's say, instead we were to give it some examples of what to generate, the generator can generate things better. So this is I think one of the examples of saying, like, you can have certain feedback, but some feedbacks are more informative than others. And in this case, like a win-loss feedback is actually one of the least informative. It's better to give the steps and everything that you can learn from. So I would say maybe the answer is yes, you can learn from competition, even without the ground truth by just pitting them in a competition. But you may not do it well. You may not learn it well. Yeah. Over here, the LM as a judge is a bit different. The LM as a judge can also provide critique. So you can learn from those critics also. It's just that you may not be sure whether this LM as a judge gives the right critique. Yeah, but at least this is more informative than learning competition-based reward. Like there's a binary win-loss, very, very hard to learn from. Okay, yeah, I think I'll leave it as that. So you are okay with this? Or you want to talk some more before we move on?
Oh no, it's fine.
Okay, let's go to the next one. Can we scale up competition to include diverse agents rather than just trajectories sampled from one? I say yes. You can do like what Derek said earlier, like role-playing agents, or you can just do agents with different contexts. And you can even do like different prompts to elicit different responses. So there are many ways to do this. I think this is a very interesting research topic because being able to generate the right trajectories is so important. And if you have strategies that can increase the generation of a good trajectory, I think that will play a huge role in improving the LM's performance. Right? Essentially, you are giving like some form of thinking framework for the LM to think in. And that's very important. Like a lot of people have made lots of money by selling thinking frameworks. Like you need to think of an idea. They need to use certain frameworks to think of the idea, like SMART ideas, SMART, measurable, actionable, and so on. Yeah, so those are certain frameworks that if you don't give me, I may not know about it. So, but if you give me that framework, then suddenly everything becomes clearer. I can interpret everything based on that framework. So this framework is very important. In fact, I advise some companies also, like if you are using LM-based products, the LM itself is not the main thing. The main thing is your procedure, your process. Can you have like a domain expert process to get from start point to end point in a very structured way that is tailored to your domain? That is the make or break, because just using LMs to generate, anyone can do it. But knowing the process to generate it, I think that can be quite difficult. That might need some expertise. So yes, I think this all makes a huge difference in how we get better trajectories here. All right, last question. Can we learn from goal-directed intermediate states? I would say yes. Just reformat the problem according to what has been done. You have a good trajectory. So this is awesome because essentially you can learn from failures in this way. And I think this increases the diversity of what you can learn from and perhaps improve the model's outputs. And the good thing is all these trajectories, all this failed but repackaged trajectories are good ones. Okay, because all reach the goal. Right. So very interesting idea. Let me know if you are interested to do experiments on this, and I can work together with you. I think this is very interesting line of approach to see whether we can learn from failures just by repackaging the goal state.
So sorry, what do you mean by fail but reach the goal state?
Oh, if you look at the previous slide, here we made an error. We actually calculated the wrong answer.
Oh, I see. The intermediate.
Yeah, but you can repackage the question as what you have done. Okay, if not, thanks for staying. I know I exceeded the 1 hour 30 minutes. But I hope you enjoyed it. I certainly did enjoy reading the R1 paper. It made me think about quite a lot of stuff. And feel free to discuss more on this. I think there's a lot of insights we can get from this paper. And the most interesting insight I got is group competition is very important, because when you can compete with a very objective way of scoring it, okay, and you reinforce the good trajectories and you de-reinforce the bad trajectories, like this diagram here, what you will get is you'll get an agent or get a model that performs better and better at a certain problem, because you reinforce the good ones. And you can reinforce them disproportionately based on how well they do above the group average, or how badly they do with respect to the group average. So I think this method of reinforcement is very interesting and very exciting, because I do feel like the brain also everywhere is competition. Whether your set of neurons are activated or not is dependent on whether or not it performs better for a task that it gets reinforced. So this essentially is quite similar to competition-based learning. I believe is happening in us as well. So great idea, and I really appreciate the DeepSeek for releasing all this open source, because we got to learn so much from it. Okay, if there's nothing else, I'll be ending it here today. Thanks for coming.